So we're talking about L'Hopital's rule, right? And I told you that in the future, I'll probably write it as L'Hospital's rule because I can't spell and I'm not very good at typing the little O thing. So let's just talk about what it says. Whenever we're given an indeterminate form, or when we plug something in and get 0 over 0 or infinity over infinity, that's when we're talking about L'Hopital's rule. Now we do have other ways that we can use to find limits when we have an indeterminate form. Remember, we factored and got that. We also were able to memorize some limits like the sine x over x. We knew that equaled 1. But then when we got to this limit, ln x over x minus 1, we were like, well, I don't know what to do. We have no tools for it yet. So we have another tool to be able to solve limits like this when we don't know what to do. And we call it L'Hopital's rule. Okay, and I said that if I have a limit of a fraction, so f over g. All right, anyone coming in need the notes from last time? All right, good. All right, I was getting kind of worried there. I was feeling a little awkward talking to 4 people. All right. Let's just say we have a limit and we have a fraction and we plug it in and we either get 0 over 0 or infinity over infinity. Only those two work, okay? You're gonna take the derivative of the top, take the derivative of the bottom, and then take the limit of that one, okay? Now, I wanna give you a little warning. This is not the quotient rule, okay? So you're not doing what the quotient rule says. You're just taking the derivative of the top and the bottom, okay? Another warning for you is always try plugging in and seeing if you have an indeterminate form first. L'Hopital's rule only works if you have 0 over 0 or infinity over infinity. It doesn't work if that doesn't happen, and we'll see that a little bit later. Let's do an example real quick. So in this example, we have the limit of ln x over x minus 1, which was the example that we didn't know how to do last time, right? Okay, if I plug things in, that's what we do first. So we plug in and see what happens. We'd get ln of 1 over 1 minus 1. What's the natural log of 1? I think I heard 0, right? The natural log of 1 is always going to be 0. And 1 minus 1 is 0. So it looks like we do have that 0 over 0 indeterminate form. Looks like we have to do a little bit more work. Okay. So let's do L'Hopital's rule. Okay. So this limit is equal to, and I'm going to put a little LH here just to be like, hey, we're using L'Hopital's rule here. Kevin, do you need the notes?
No.
Okay, good. Okay. So this is the same as the limit as x goes to 1. And we have to do the derivative of the top. What's the derivative of ln of x? 1 over x, right? That's the one we had to memorize. And what's the derivative of x minus 1? 1, good. Okay, so let me just clean this up a little bit. This is the limit as x goes to 1 of, well, just 1 over x, right? Okay. Now we have a limit that we know how to solve. Do you have the notes from last time?
No, I don't want to.
Yeah. Oh. Oh, we can just keep it. I have plenty of copies. Okay, once we're here, and we have the limit as x goes to 1 of 1 over x, we can just try plugging in again, right? So just try plugging in. We have 1 over 1, and that works, right? That's not an indeterminate form. We know what that number is. It's just 1, okay? So we just used L'Hopital's rule once, and we got the answer. Any questions on using L'Hopital's rule so far? All right, seems kind of easy. I promise you L'Hopital's rule gets a lot harder, and we'll see why. But let's just do a couple more easy ones to get ourselves in the right headspace here. I'm going to do one more before I leave you on your own here. Let's do this one. We have e to the x over x squared as we go to infinity, okay? Remember, always plug in first to see what type of indeterminate form we might have. Plugging in, we have e to the infinity over infinity squared. Okay. What is e to the infinity going to? positive infinity, right? And if you don't remember why it's infinity, you can just think about the graph of e to the x, right? So that's what the graph looks like. As we go to infinity, that graph is going all the way up to infinity, okay? So this is definitely going to positive infinity up top. And what do you think infinity squared is going to? Also positive infinity, right? It's definitely going to a really big number, right? So that's definitely infinity. So remember, we said infinity over infinity is still an indeterminate form. So that gives us a reason to do a L'Hopital's rule again, okay? So let's do this. We know using L'Hopital's rule, I'm just gonna write it above the equal sign so we know we're using L'Hopital's rule here. I'm just gonna keep the limit the same and then take the derivative of the top and the bottom. What's the derivative of e to the x? E to the x, good. And what's the derivative of x squared? 2x, good. Okay, we have a new limit. Let's plug in and see if we get a nice answer here. Plugging in, we have e to the infinity over 2 times infinity. Okay. E to the infinity, we already said was infinity. What do you think 2 times infinity is going to? Infinity, right? Oh, looks like we have another indeterminate form. So did L'Hopital's rule kind of fail here? No, what do you think we should do? Yeah, do it again, right? Do L'Hopital's rule again. So let's do L'Hopital's rule again. Okay, so now we're doing it twice. So we got the limit as x goes to infinity. Derivative of e to the x is still e to the x. What's the derivative of 2x? 2, good. All right. Yep, let's plug in again. We've got e to the infinity over 2. Okay, we said e to the infinity is infinity over 2. What do you think this is? Infinity, right? Infinity divided by anything is still infinity. The only reason it would be weird is if it was an indeterminate form, which is infinity over infinity. Okay, so this is still positive infinity. Looks like that's our answer. Okay, so some things I want you to note. L'Hopital's rule is derivative of the top over the derivative of the bottom. It's not quotient rule. I know it's very tempting to do quotient rule here. Don't do it, okay? I want you to try example number 5. Okay, very similar to what we did before. And if you're done that, you can try example number 6 too. Okay, I think everyone's good on example 5 except maybe simplifying. So why don't I show you example 5 in kind of more detail and show you the trick I do to do this. Okay. So example number 5, when we plug things in, we got ln of infinity over the square root of infinity, right? What's the natural log of infinity? Just infinity, right? The natural log function looks like this, right? So as we go towards x values that are really big, those y values are also getting really big. So this is infinity. What's the square root of infinity? Infinity, right? The square root function looks like this. And as we get really, really high numbers, like the square root of like 1 billion, it's still going to be a really big number. So that's still going to be infinity. This is an indeterminate form, so we can use L'Hopital's rule. Okay. And I think everyone got to the point. Let me do this in more detail. I think everyone knows that the derivative of the natural log is 1 over x, right? We all got that. Okay. Next, this is kind of a little bit of a review here, but the square root of x is x to the 1/2, right? So if I were to take this derivative, it'd be 1/2 times x to the negative 1/2. Right, are we good with that? Good. Okay, now we have a fraction and then we have another fraction and then like something that's not in the fraction. That's kind of confusing. What I like to do when I have this is I'm going to make the top part a fraction, which it already is, and then I'm going to make the bottom part of the big fraction one big fraction. Okay, and if that doesn't make sense, let's just do it step by step. Okay. Oh, I forgot to write the limit here. LH limit as x goes to infinity. Okay, so let me just simplify this. Okay, I'm going to do it one step at a time here. We have 1 over x. We have a half. What's another way of saying x to the negative 1/2?
X is negative 1 over 2 times square root of x.
Okay, I see you put it all together, but x to the negative 1/2, taking away the negative would bring the x to the 1/2 in the bottom, right? So everyone see how x to the negative 1/2 becomes 1 over x to the 1/2? I know it's in the fraction, but that's kind of a thing we do with powers, right? Okay, once we're here, let's just combine the 1/2 and the x to the 1/2, right? So we can do this, 1 over x, 1 over 2 x to the 1/2, right? So I just multiplied through with that fraction. So what I've done here is if I took the original fraction and I've kind of combined the bottom fraction into one big fraction, okay? So now we have a fraction divided by another fraction. Is everyone good how I got here? Good. Okay, once we're here, let's make this one fraction now, okay? Now, I don't know, actually someone taught me this last semester, but what we can do is keep the first one the same. So change the division into multiplication, right? So change, and then flip the bottom fraction over. So find the reciprocal. So 2x to the 1/2 over 1. So keep, change, flip this fraction, okay? All right, what we're left with is the limit as x goes to infinity of 2x to the 1/2 over x. Okay. So now we're a little bit more simplified. Does everyone kind of see how I simplified everything? Yeah.
After that, do you have like, when you go again with L'Hopital's rule, how do you take a derivative of that, or you go back to the original one?
Oh, we actually don't have to go again with L'Hopital's rule.
Really?
Yeah, let me show you. If we simplified even more, you'll see why. Let's try it again. So I know that the 2x to the 1/2. What's another way of saying 1/2 power? Square root, right? So this is the same as the 2 square root of x over x. Okay. Now I have an x up top. I have an x in the bottom. I can kind of cross out the x on top and then change the bottom to the square root of x, right? So I'm just kind of simplifying it a little bit, okay? So what I'm left with is the limit as x goes to infinity of 2 over the square root of x, right? All right, are we good here? Good, okay. Once we're here, I know it's tempting to do L'Hopital's rule again. Before we do it, let's just plug in and see if what we get is an actual answer, okay? So let me just plug in. Let me use a different color here. Maybe not purple. Plugging in. This will give me 2 over the square root of infinity. We said that the square root of infinity is infinity. What's 2 divided by a really big number? What's that going to be?
Positive.
It's going to be positive. Well,
It's gonna be very small.
it's going to be very small, right? So it's going to be a very small positive number. Now, if it's infinity, the biggest number you can ever think of, this is going to 0, right? Okay, so this is actually 0. That's our final answer. We know 0 is not an indeterminate form. It's a real answer. So you don't have to do L'Hopital's rule again.
So divided by infinity is going to 0.
Yeah, so the limit as x goes to infinity of any fraction, so 1 over x, 1 over x squared, 1 over the square root of x, something like that is going to go to 0, okay? You can even think of it as the graph of 1 over x kind of looks like this. That's going to 0 as we plug in really big numbers. All right, any questions on example number 5? Yeah.
Can you go back to when it goes from 1 over x over 1 over 2 to x to the 1/2?
Yeah, so how we went from here to here?
Yeah, basically that entire, most of that line.
Yeah, so I know it's kind of confusing with numbers. Let me do it with let me show you what to do if it's just like regular numbers. I feel like that's a little bit easier to understand. Let's do this. What if we had, I don't know, 5/6 over 7/8? Okay, let's see how we can simplify this, okay? Whenever we see this, you always keep the first fraction, okay? So you're gonna keep the 5/6, change the division sign to multiplication, okay? And then flip over the bottom fraction, so 8/7. Okay, this is kind of a standard procedure when you divide a fraction by a fraction. You're technically just multiplying by the reciprocal of the bottom, okay? So the same thing happens with not fractions, right? So I basically kept the 1/x by itself. I changed the division to multiplication, and then I flipped the other fraction over. So, all right, does that kind of help?
Yeah.
Oh, do I have a question? Nope. All right, why don't you try example number 6? This one might be a little bit easier depending on how comfortable you are with trig functions. Yeah, let's do some practice with example number 6 next. Yeah.
Five.
Mhm.
Would it be not 2/x, but 1/x?
Which one?
Like that's the last time you did the derivative on top and bottom.
He's wondering how you got the square root of the denominator when you have it divided by x.
So here?
No,
Oh, so lower? So here?
just to the right, where it's 2 square root of x divided by x.
Uh-huh. Oh, so you're wondering how the square root of x ended up in the bottom when I did this?
No, I understand how it got to the bottom.
Uh-huh.
It's just a 2. Like that 2 should be a 1 at that point. It's
No, I think the 2 should stay there, right?
I mean, you have to do the derivative in order to get that square root on the bottom.
Oh, I didn't do the derivative from here to here. I just simplified. So here, I'm not doing L'Hopital's rule here. I only did it one time. Right, so I only did L'Hopital's rule once, and that was up here. So no derivatives happen from here to here. Does that make sense? Yeah, here, all I did was cancel. I noticed that there was an x on the bottom. That's an x to the first power. Up here, it's an x to the 1/2 power. So I just canceled out the one on top, and the bottom one turned into the square root of x. So let me show this in more detail here. We have the limit as x goes to infinity. Oh, you get it? Okay. I know fractions are just, I put a lot of fractions in that one. All right, let's go to example number 6. I'll give you a few minutes to try this one. And I do want to go through these in a little bit more detail, so I'm not going to ask anyone to write up their answer yet. Let's just go over how we do this one real quick. Okay. So finding the limit of x squared over 1 minus cosine x, the first thing we want to do is just plug in and see what happens, right? So 0 squared over 1 minus cosine of 0. 0 squared is 0. What's cosine of 0? 1, good. John, do you need the notes from last class?
From last class.
Okay, good. So this is really a 0/0 type limit, right? So we know that we have to do L'Hopital's rule, okay? So let's just do that, L'Hopital's rule. The limit as x goes to 0, the derivative, what's the derivative of x squared? 2x, good. And how do I find the derivative of 1 minus cosine x? Well, maybe we can take it step by step. What's the derivative of 1? I think I heard a 0, right? Derivative of 1 is 0, so I'll even write that out. And then we're doing minus. What's the derivative of cosine?
Negative sine x.
Negative sine x, good. So 1 minus negative, 0 minus negative sine x. Okay, let me clean this up here. This would be the limit as x goes to 0 of 2x over positive sine x. Okay. So now that we're here, it's cleaned up a little bit. Let's just plug in and see what happens. We have 2 times 0, which is definitely 0. And then this is over the sine of 0. Okay. What's the sine of 0? I think I heard it 0, right? Okay, so we definitely have a 0 over 0 type limit again. So what do we have to do?
I'll go through the L'Hopital's rule one more time.
Go through L'Hopital's rule one more time, right? We got to do it again. All right, so L'Hopital's rule again. We have to do the limit as x goes to 0. What's the derivative of 2x? 2, I heard it. All right. And what's the derivative of sine x? Positive cosine x. Good. Okay. Again, we've cleaned it up already, so let's plug in. I guess plugging in 0 would be 2 over the cosine of 0. Whoop. Oh gosh. Okay, well, let me try this again. Okay, 2 over the cosine of 0. What's the cosine of 0? 1, good. So 2 is actually our answer. That's it. All right. Any questions on example number 6? Perfect. Okay. Why don't we do example number 7? I'm actually going to do this with you. And what I'm going to do is I'm actually going to make a mistake, and I want you to see if you can catch it. Okay. All right. So let's see this one. It's sine x over 1 minus cosine x. And let's say I'm a student. I have this on my test, and I'm going to try to see if this works. Okay. So I'm going to do L'Hopital's rule, and I'm going to do the limit as x goes to pi from the left. By the way, L'Hopital's rule works fine with left and right limits, so don't worry about the left, the minus sign there. Okay. The derivative of sine x is cosine x. And the derivative of 1 minus cosine x is 0 minus negative sine x, right? Okay, so cleaning this up, this is the limit as x goes to pi from the left of cosine x over sine x. Okay, now that I have it in the right form, I can plug in pi. Okay, this is cosine of pi over sine pi, which gives me, what's cosine of pi? -1. What's sine of pi? 0. And what's that going to if I divide by a small number like 0? Does not exist, or it goes to basically infinity, or in this case, maybe negative infinity, right? That's where this one's going to. Okay. So what did I do wrong here? Troy?
Can you not use the L'Hopital or whatever? If it's like not 0 or infinity.
Okay, so can you elaborate on that a little bit?
Doesn't the rule state that the limit has to be approaching 0 or infinity?
I got the plug-in. That's what he's trying to say.
Yeah, right. What Troy's trying to say is I forgot to plug in first. The first step to doing L'Hopital's rule is you have to plug in the number into your original function, see what it is, and you can only use L'Hopital's rule if it's 0 over 0 or infinity over infinity. That's the only time you can use it. So let's just plug in and see what happens. Okay. So plugging in pi, this is the sine of pi over 1 minus cosine pi. We said before that the sine of pi was 0, right? And we said that cosine pi is -1, so 1 minus -1. 0 over 2 is 0. Okay, so if I just plug into the original function, I get 0. That's my answer. Okay, so I did all this work to get the wrong answer at the end. Okay, so what I want you to do is if you are copying what I wrote down, please X out or cross out what I wrote here, because that's not the right way to do the question. Okay, always plug in first, see if you get an answer that's not an indeterminate form. If it's not, then you don't have to do L'Hopital's rule. Actually, if you do it, you're going to get the wrong answer. Okay. All right. Any questions on example number 7? All right, good. I think we're all trained on that. Why don't we talk about a different type of question here? Okay. So let's go to the next page. On the top here, I'm going to tell you about 2 things that we've talked about so far. We talked about indeterminate forms that look like this: 0 over 0 or infinity over infinity. I'm gonna tell you that there's other indeterminate forms that don't look like this, okay? And I'll give you an example, okay? Here we have the limit as x goes to 0 from the right, don't worry about right versus left, of x times the natural log of x. Well, I said the first thing we have to do is to plug in, right? So plugging in 0, we have 0 times the natural log of 0, right? What's the natural log of 0 going to? It doesn't exist. And if you take a look at the graph of the natural log, like if you had your calculator or something, it would look like this, right? And I know that as I'm approaching 0 from the right, where is the natural log function going to? Negative infinity, right? So this is really going to 0 times negative infinity, okay? Now, doesn't look like 0, 0 or infinity, but this is actually another type of indeterminate form, okay? So this is an indeterminate form. Okay, and basically anything that looks like 0 times infinity or 0 times negative infinity, that's another type of indeterminate form. Okay, so not just 0 over 0 or infinity, we can also have 0 times plus or minus infinity. Okay, now there's actually 7 types of indeterminate forms. We have 3 now, and we'll learn how to do the rest of them throughout class. All right, let's figure out what we do with indeterminate products, okay? Any ideas on what we can do here?
Take the derivative.
We can take the derivative, but that's not really what L'Hopital's rule tells us to do, right? L'Hopital's rule only works with when we have a fraction. Maybe we can make it look like a fraction, right? Do you think I can change my function to look like a function over another function?
Can you put it over 1?
If I put it over 1, it will change the entire function. So I want to keep the function the same, but represent it using fractions.
You can do funny stuff with natural log and like log-based stuff.
We're getting there, but not for this type of indeterminate product or indeterminate form. Let me show you a little trick here. Okay, so I'm going to keep my limit the same, but instead of writing x, I'm going to write this: 1 over x. Isn't that the same thing as writing x?
Yeah.
Yeah, right. So another way this is a trick that kind of always goes with indeterminate products, is instead of writing x, we're going to write 1 over x. Okay, so I'm going to multiply this by ln of x. Okay, and if that looks weird to you, why don't we do this? I'm just going to move the x to the denominator and make this the natural log of x over 1 over x. Okay, I know it looks funny, but what I wrote here is the same thing as my product. Okay, so this is the same thing as saying x times ln of x. Everyone kind of see this. Good. All right, let's plug in and see if we get 0 over 0 or infinity over infinity. Okay, so we got the natural log of 0 over 1 over 0. We said earlier in the question that the natural log of 0 is going to negative infinity. And then what is 1 over 0 going to? Infinity, like positive infinity, right? Okay, so it looks like we do have infinity over infinity, which is an indeterminate form, right? That's one that we know we can use L'Hopital's rule with. So now that we have it in this form, we can use L'Hopital's rule. Okay. Okay, so what's the derivative of natural log? 1 over x, good. And instead of finding the derivative of 1 over x, which I know is kind of weird, let's just rewrite 1 over x as x to the negative 1. Okay, what's the derivative of x to the negative 1?
Negative x to the negative 2.
Yep, negative x to the negative 2. Good. All right, if you're not good with flipping over fractions in your head, what I like to do is always represent this as a fraction over another fraction, okay? So what I'm going to do is I'm going to keep the 1 over x the same, and then change the x to the negative 2 to negative 1 over x squared, Okay, so the bottom just becomes a fraction. All right, once I'm here, I can keep, change, and flip. So I'm gonna keep the first fraction the same. So keep the 1/x, change the division to multiplication. So change, and then I'm gonna flip the bottom to -x²/1. Okay, so keep, change, flip. Simplifying this gives me the limit as x goes to 0 of -x²/x. Once I'm here, let's just simplify things, make it look a little bit better. So this is the limit as x goes to 0 from the right of, I think it's just -x, right? Simplifying that. Once we're here, looks like we've simplified enough, so we can plug in. Plugging in, we have -0, which is 0. And that's my final answer. All right. Any question on example number 8? Okay, so the thing with indeterminate products is we basically see that it's an indeterminate product because we know it's 0 times infinity. We change it into a fraction. So we do something with the properties of exponents to make it a fraction, like how we got x to 1/x on the bottom. And then we just do L'Hopital's rule as normal. Okay, now I have a little explanation on the bottom here. Basically, what I have here is how we do indeterminate products. Okay, if you see 0 times plus or minus infinity, you're going to first plug in, see if you have it. Okay, you're going to rewrite the product as a fraction. Okay, and the way you're going to do that is either using properties of exponents, which we just did. The other way you can do this is use trig identities, which we'll see tomorrow. Okay, so I'll do an example with trig tomorrow. Okay, once it's written as a quotient, we can do L'Hopital's rule as normal. Okay. All right, that was a lot of talking on my part. Any questions on example 8? All right, then what we'll do is, I think we got a quiz review to go over, so let's do that.